Hello students, welcome to Brushti Sir's classes. Sir again, Brushti Sir is going to take a new concept today. Last class I discussed about the irrotational flow, non-rotational flow or ideal fluid negotiating a bend, and the R into V was constant while at the bend section. It was a horizontal bend. Do you remember that? Okay. Do you remember that? Okay. Now, what happens when a non-ideal liquid flows? What do you mean by non-ideal liquid? Means viscosity is present. Just see this. I have drawn a diagram here. As you can see, this is a non-ideal liquid kept in a container which is open to atmosphere, and container is rotating about its axis of symmetry with a constant angular velocity omega. Omega is the angular velocity of the container. So if we rotate it, the container, the fluids will get, will they rotate? Suppose this is an ideal fluid, ideal liquid. So ideal liquid, what will happen? If the container rotates, the container wall, which will be touching the layer of the liquid here, layer after layer, the liquid will be, this one liquid layer will be here. That is the outermost liquid layer. Then next one, another liquid layer, another liquid layer. All the container wall cannot drag the touching liquid layer itself because viscous force is not there, viscosity is absent. So only container goes on rotating, whereas no liquid layers. I am imagining an infinite number of cylindrical layers of this liquid. None of them will be set into rotation because there is no tangential force, means no viscous force acting on any of them. The last layer, the touching layer cannot drag the second layer, there's no viscous force. Second layer cannot drag the third layer, no viscous force. Yes or no? So the container will only rotate, but liquid cannot rotate. Liquid will be stationary, and the surface of the liquid will remain flat as before, even if the container rotates, because it's an ideal liquid. There is no force to rotate it, no tangential force to make the rotation, to start the rotation for any of the liquid layers. Am I clear? But if it is a real liquid, means a non-ideal liquid, that viscosity is there. So the viscous force will act on the touching layer, absolutely no issues. So it will drag the touching layer along with it because there won't be any relative motion between the touching layer and the liquid wall and the container wall. Then layer 1 will drag the layer 2 along with it. Layer 2 will drag the layer 3 along with it. So as a result, all the layers, they go on rotating. In a steady state condition, all the layers attain same omega, same angular velocity omega. They are at steady state. Okay, this is only for non-ideal liquid. Ideal liquid will not be affected at all by the rotation of the container. Now, if the liquid layers rotate, then this particular flat surface, a horizontal flat surface, will not remain flat. Why? You place yourself here as an observer. You notice here, take a fluid element. You are in a rotating frame. What forces you will see? In addition to that, for unit mass, the vertical force will be G. This is the gravity force on the unit mass. This is the unit mass. And there is a centrifugal force per unit mass. That is omega square x will act. So the resultant force will be like this only. And the force on the surface must be perpendicular to the surface at steady condition, because liquid cannot withstand any tangential force at the surface. So if any force is there, that must be normal to the surface. So surface bends such that it will become normal here. This will become bent, that's why the force becomes normal here. So like this, the surface will take a shape like this, as shown here. Let me draw it here. G omega square x G is the resultant force. Is the resultant force Fr. This is the tangent to the surface. So this angle is theta. It makes angle theta with the horizontal. So this is same angle theta here. So dy by dx, if this is my y and this is my x, the lowest, this point is my x, then dy by dx of the slope of this surface at this point must be tan theta. That must be equal to this line by this length by this length, that is omega square x by g. So obviously dy will be omega square x by g into dx. Integrating y will be omega square by 2g into x square plus c. But as you can see here, at x is equal to 0, I've chosen my x-axis here. X is equal to 0, y is 0, this is 0, 0 point. So at x0, y0, this itself is the equation of a parabola. So if I put at x, at lowest point of the parabola, if I take the origin, then x0, y0, then I get c also 0. So what I get then, the final equation, y is equal to omega square x square by 2g. This is a parabolic curve. Agreed. So this is the surface. This is the parabolic surface. In 3-dimensional, it looks like a paraboloid, because I am showing a 2-dimension, but it's a 3-dimensional body. So the parabola revolving around this symmetric axis will build a paraboloid surface. right? Okay. Then let us come to our discussion here. Since all the liquids, all the layers are moving with same omega, then I take two streamlines here. I take two streamlines. That is streamline 1 and streamline 2. Okay. So for streamlines, what we write as equation, Bernoulli's theorem. For every streamline, is a rotational flow? Yes. Here I want to just point out a very significant fact. As all the liquid layers go on rotating with omega, then at steady condition, even if they are moving, so there will be no sliding. There will be no sliding. No sliding between the layers. They all are moving with same omega. So if any viscosity is there, viscous force will become 0. Viscous force becomes 0. Is it okay? So this becomes a inviscid flow. Viscosity is still there. It is a real liquid, but viscous force is not acting in the flow condition. Non-viscous flow. So viscous liquid, but flow is non-viscous. आप पूछेंगे भाई ये कैसी बात है? You have seen this in normal mechanics also. Suppose there is a conveyor belt. It is moving. You drop a cube on the conveyor belt. It will drag it. Because friction force, the sliding friction will act between conveyor belt and the cube. But as the cube, that cubical block gains velocity and velocity becomes equal to that of the conveyor belt, there will be no slipping between the conveyor belt and the block, and there will be the friction force which is acting till now will simply vanish. So friction coefficient is there. Surface is still rough, but this friction force is not there. You must have noticed that. Similar here only. Viscosity is present, but viscous force is not acting while this steady state condition is reached. And in that steady state condition, the top surface is parabolic and equation is this. Am I clear? Okay, now come to these two streamline flows. And this is a rotational flow and two streamlines in rotational flow. So for streamline 1, I write for streamline 1, बोलो क्या लिखेंगे भाई? बर्नौली's theorem, what should I write? P1 by rho V1 square by 2 plus G into H1 is C1. Again, I'm telling you, both of them are same. Two streamlines I'm taking in the same plane, same horizontal plane. That means H1 and H2 are equal. Okay. But for streamline 1, it is H1. Streamline 2, it is H2. We can now for streamline 2, let us write. For streamline 2, P2 by rho plus V2 square by G A2 plus G H2 is total energy per unit mass C2. Let us call this. In ideal fluid case, in irrotational flow, C1 is equal to C2. Yesterday we have seen this. Last class we have seen this. But here, let us see, are they same? Now P1. What is P1 here? P atmospheric. This is PA. This is P atmospheric plus rho G Y1. And Y2 is greater than Y1 because it's a parabola and its height is, the surface is rising towards this radius of the content. Yes or no? So P1 is PA plus rho G Y1. What is P2? PA plus rho G Y2. अभी velocity में आ जाओ बेटा. All are moving with same omega. If the radius is R1, this radius R1 and this radius R2. So R2 bigger than R1. It is something like this. I've seen roughly this one. Now you can imagine here. This is the this is R1. This is R2. So this is omega. Each liquid circle, each circular paths. This is circular streamline. All circular streamlines are rotating with same omega. So V1 I'll write as omega R1 and V2 I'll write as omega R2. Okay. And this is your H1. Sorry, Y1. This is your Y2. Obviously, Y2 is greater than H1, H2. This is H1. This is H2. Horizontal height. The vertical height of this streamlines from the ground level. Okay, so H1 equal to H2. So now compare the C1, C2. So this by comparison you get Y2 greater than Y1. Y2 greater than Y1 implies P2 greater than P1. R2 greater than R1 implies V2 greater than V1. GH1 is equal to GH2. That means if I compare, C2 will be greater than C1. Obviously, this term is greater than GH1. It is GH1 equal to GH2. V2 square is greater than V1 square. P2 greater than P1. So obviously C2 will be greater than C2. Just see in the rotational flow, I found that the two streamlines in the same rotational flow, their total energy per unit mass, they are different. Are you understanding this? In previous example, when the flow was irrotational, I told this is the flow. streamline flow of an ideal fluid. I told this is 1, this is 2. So this was my center of curvature. This is the center of curvature. This is the R1, R2. I was recapitulating what I did last class. So this I told for any other layer, any layer here, this radius is R and the velocity is V. This is R2 is here. This is R and V. So RV is constant for the irrotational flow. For rotational flow, what is constant? Omega same. So here it shows, here I'll write V by R is omega is constant. The V by R is constant for this. But in irrotational fluid is VR is constant. Are you observing? VR is constant in irrotational fluid. And as I told you last class, I'll explain you that the V by rho plus V square by 2 plus GH is constant along a streamline. Whether the flow is rotational or irrotational, along a streamline, it is constant. Provided the viscous force is not doing any work. Here, there is no viscous force in the infinite flow, so no viscous force doing any work. Even if viscosity might be present, it is present. But the viscous, the C1 and C2, they are different. Whereas in the irrotational flow, for every streamline, C1, C2, C3, C4, C4, any streamline you say, it is constant only for all streamlines. Along a streamlines, whatever constant, any other streamline also same constant. But here what it is? From streamline to streamline, the total energy per unit mass may not be constant. It is varying from streamline to streamline. This is observed here. Understood this? This is what I wanted you to know. Here, VR was constant. In the here, V by R is omega is constant, but here it is VR is constant. VR is constant. Here it is V by R is constant. Am I clear? Is it interesting or not? So now we have discussed something very, very important point in fluid dynamics. So this point, the constant, that's total energy per unit mass, is constant along a streamline. That is what is given by Bernoulli's theorem. But Bernoulli's theorem never compares the total energy per unit mass between streamlines, because Bernoulli's theorem, using Bernoulli's theorem, we cannot arrive at that result. That requires the fluid kinematics, which in turn requires some mathematical prerequisites which we have not studied till now. So, okay, so we will, so what we have discussed here is going to be very important for you. So what we have discussed here is going to be very important for you in future applications. We'll also discuss how much it will come down, this lowest point, how much will go up if it is a circular cross-section container. That we'll do later. But first you have understood this in this way. You must have known this, but we have derived it for you. Absolutely no issues. Just take the pseudo forces, then the gravity force resultant will be making angle, making a 90-degree angle with the surface. It makes a theta angle with the g. So dy by dx to the surface makes n theta from the geometry. So dy by dx is tan theta, and tan theta is omega square x by g. Beautiful. Okay, fine. But more important, what I want to discuss this C2 is not same as, and in this rotational flow, V by R constant, not VR is not constant, because VR is constant in the irrotational while negotiating a bend. Okay, we'll stop here, students. I hope you like this. I'll come again, one more important point. Bernoulli's theorem application in a rotating reference, that we'll discuss next class. Okay, so these my credentials, this is the topic. All of you are clear. Thank you all. We'll stop today. All the best to you.